Okay, so thanks very much for inviting me to speak at this conference. Okay, so let me first write down the title, Spectral Side of Stable Local Trace Formula for Real Groups. Okay, so to begin with, so let's take G to be a connected reductive group over a local field F. So this is local of characteristic 0. Eventually, we'll consider the real field case, okay? But for the first part, okay, it's over local, any local field. Okay? And we will look at the L2 space of G of F. And here we have the regular representation of GF cross GF given by, so if we have say a pair of elements G1, G2, so the regular action on a L2 function, all right? Okay, so the value, say at a y in GF is then given by, so basically combining the right regular action of this copy of G of F and the left regular action of this copy of G of F. Okay, so. Yeah. In the beginning part, any local field, p-adic or Archimedean. But eventually, I only look at the Archimedean case. Okay, right. So we want to, of course, we want to study the trace formula in this setting, which is the local trace formula. In this case, so this is the local trace formula, which in general was established by Arthur. Okay, yeah. So let us just briefly review the setup. So let's say that we have a pair, a test function, and in this case, because we have two copies of G of F, so this corresponds to, say, a pair of test functions, so F1 and F2, smooth functions with compact support in G of F, and to be precise, in the Hacker space when F is Archimedean. Okay, and just a little bit more convenient to do this. So here just means complex conjugate. Okay, so for a function f, test function like this, so if you look at the operator, so the regular representation, okay, that you define using this test function. So this has kernel, the operator has kernel given by, so kf, xy, so here xy are in G of F. So it has the following formula. Yeah. Yes, in the real case is in the Hacker space. Okay, so yeah, okay, yeah. So for xy in GF, so we have the kernel, so given by this formula. Okay, and then just as in the global automorphic setting, so we hope to construct a trace formula by integrating the kernel along the diagonal and then developing both the spectral and geometric expansions. Okay, so in other words, we look at, you integrate the kernel over the diagonal, all right, and then you develop the spectral and geometric expansions for this. And of course, when G of F is not compact, then one has to make sense of this integral by suitable truncation procedure. But let's just, as an example, look at a case when G is anisotropic over F. So therefore, G of F is just compact. Okay, so example, so if G of F is compact, then of course this integral makes sense. In that case, we can develop, so for example, for the geometric expansion, just as a consequence of the Weyl integration formula, so just by, essentially just by Weyl integration formula, okay, so then the geometric expansion is expressed as an integral over the conjugacy class. So yes, okay, so integral over, more precisely, okay, the regular conjugacy class G of f. Okay, so it's an integral over a conjugate class over the orbital integrals of our pair of test function f1 and f2. Okay, so let me write in this way. So here, these are just orbital integrals. Okay, so fi of gamma and here, just as usual, we normalize it by the Weyl discriminants, square root. Okay, yeah. So on the other hand, for the spectral side, then it is we just develop the spectral expansion using the Peter-Weyl theorem. Okay, so for the spectral side, so just by Peter-Weyl theorem. Okay, so namely that when G of f is compact, so we have this decomposition of the L2 space, so as a GF cross GF module. Okay, so direct sum, pi, that's a pi du. Okay. Or to be precise, Hilbert space direct sum. Maybe I write this way. Okay, pi tensor pi contragradient, where pi is over the irreducible representation of G of f. Okay, and so therefore the spectral expansion just looks like this. Spectral expansion of this trace formula. Sum over pi for our test function as before, f1 cross f2 conjugate. Okay, so trace of pi of f1 times trace of pi f2. Complex conjugate. Okay, right. So this is the case when G of f is compact, and of course, naturally, so when this condition is not satisfied, then we need just as in Jasmine talk, previous talk, so we need to perform a truncation on the kernel, okay, and then you develop the spectral and geometric expansion for this. Okay, so when you do a truncation, then this is this integral converges absolutely. So, but there's a problem, because when we do a truncation procedure, then the truncation is not an invariant procedure. So in this case, in the previous case, all these distributions are invariant under conjugation by G of f. Okay. So, and when we do this, then the invariant property is lost. So, for example, in the geometric side, so there would be so-called, so we got extra terms. So these are called weighted orbital integrals. So in Arthur's notation, it looks like that. So here M is a Levy subgroup of G. So these are not invariants. So these are not invariant under GF conjugation. And so there's a procedure, so as defined by Arthur, of rendering these become invariant. So the invariant version so which alpha denoted in this way. So however, it should be said that this procedure by itself actually is defined in terms of spectral information, more precisely the weighted characters, which occurs on the spectral side of this expansion. Okay, so then these invariant version of the weighted orbital integral were defined by certain inductive procedure, which in some sense mixes the information coming from the weighted orbital integral and the weighted character. So therefore, in the following, even though when I refer to the geometric side of the invariant local trace formula, but to be honest, it's really a mixture of both the geometric and spectral information. So in any case, so the general case of the local trace formula, as established by Arthur, okay, so general case of the invariant local trace formula. That also, of course, due to Arthur. So let me first describe the geometric side. And for simplicity, so I'm just for the sake of simplicity of exposition, I'm going to assume that the AG, so which is the F-split component of the center of G. So I'm going to assume that this is trivial. All right, okay. So the geometric side, so here's a sum. Okay, I first fix a M naught. So this is a minimal Levy subgroup of G over F. And then as in the trace formula, so we have this denote the set of Levy subgroups of G over F that contains M naught, okay? So here, so in the geometric expansion, we got a sum over the levies in this set. In the case when M, the levy, equals to G itself, then it is precisely the form that we have seen before in the case of GF is compact. So namely, it goes as follows. So the geometric side of the invariant local trace formula. So here's the following expansion. All right, so M is a levy, and this A of M is similar to this one, namely the maximal F-split component of the center of M. And of course, under our assumption, this of course is just 0, but in any case, I put it here. Okay, and then a certain numerical factors. So the vowel group of M respect to M naught, and then also the vowel group of G respect to M naught. Okay, and then here you got something similar. Okay, so over such a levy containing M naught, so you integrate over the G regular elliptic conjugacy class in M of F, and then you integrate over these distributions, okay? So IMG gamma F d gamma. Here, as we have used before, our test function has this form, okay? Yeah. In the case when M is G, then as I just said, when M is G, then this distribution, so is exactly as we have seen before, product of the usual orbital integrals. Okay. But for M not equal to G is much more complicated. As I said, okay, when M is not equal to G, actually it's a mixture of both the information coming from weighted orbital integral and weighted characters. Okay. Yeah. So this is the geometric side. Okay. So let me describe this spectral side. Okay. And this will be referred to as the discrete component of the local trace formula. So in the spectral expansion, we'll find contribution. Certainly there will be contribution coming from the discrete series, but there are more terms. Okay, so it takes some more time to describe because this is also fairly complicated. Okay, as before, our test function is formed. Okay, so the spectral expansion, which we refer to as a discrete component of the local trace formula, has this form. So let me first write down and then explain the terms involved. All right, so let me proceed with explaining. So notice that this is only a sum, okay? So in the geometric side it's an integral, right? So but here on the spectral side is only a sum, okay? So that's why we call it discrete component. So let me first proceed to explain the terms involved. So here M is as before, M is in L, so namely it's a Levy subgroup of G that containing this fixed minimal Levy, M naught. Pi is a discrete series representation of M of M. Okay. So in particular, if M is G, then here you have contribution coming from discrete series representation. Basically, in the case of M is G, this is nothing other than what we have seen before in the context of when G of F is compact. Okay? Yeah. R is an element in the so-called R group of Harris-Chandler. Okay, so R group of pi. Okay, so this is R group. So what it is? Okay, so all right. So let me proceed to explain. Here, W pi, the vowel group pi. So this is the pi. So this is the elements. So these are the elements W in the vowel group of G respect to M such that W preserves pi. All right, and attached to such an element W, we have a for W. Oops, okay, for W in W pi, we have the normalized intertwining operator. So this is normalized intertwining operator. On the parabolic induction of pi. Okay, remember this small pi is a discrete series representation of M, okay, and you take the parabolic induction, okay, and in general, this need not be irreducible, okay, yeah. And W pi naught is the subgroup, the normal subgroup, this subgroup, such that the intertwining operator is a scalar subgroup of W pi. Okay. So, maybe let me write this. Okay. So consists of the W in W pi such that the normalized intertwining operator is a scalar. Okay. Now, there are very delicate issues concerning the normalization of these intertwining operator. Okay. So here, once again, for simplicity of exposition, we are going to make the following assumption. So we assume for simplicity that the following is true. So namely that the map, so here, so W, so you send to this intertwining operator, which is in fact, it's a unitary operator on the parabolic induction. But we are going to make this assumption. So we assume that this actually induce a homomorphism on the R group to the algebra of intertwining operators. So we assume that actually induces, or actually give rise to, so induces homomorphism from the R group, which, as you recall, is the Debye quotient by the Debye knot, okay, to this algebra of intertwining operators. So, of course, this map on the face of it gives rise to a projective representation of the R group to the algebra of intertwining operators, right? Okay, so therefore, what one needs in general is really to, in order to have this, one actually pass to a finite central extension of the R group. So namely that instead of this on the nose, one really takes a certain central extension of the R group, okay, on this. Okay. However, for our case, we assume this. In fact, because we are eventually specializing to the case of real groups, this is okay by the works of Knapp. So for real groups, this is okay by Knapp. I should also mention that the normalization of these intertwining operator is very much a important, in some sense, a important problem in important issues in the study of trace formula. Okay, so in the particular case when when G is quasi-split and the representation involved have a Whittaker model, then the normalizing factors, they were given by Shahidi's local coefficients. Okay, so for example, in the case of real group, Shahidi also showed that they are given in terms of the formula, in terms of L and epsilon factors. Okay, so in general, Arthur showed that this is okay. Okay, so you can do this, and Knapp also tells us that in the case of real groups, we accept this condition. Okay, I want just explain this one more condition. Okay, so remember that I need this condition, right? Tau being this triple, M pi R being in here. So there are certain discreteness condition here. So this condition here concerns the following. So this means that if you look at the following sets, pi R, okay, so which is just the coset, okay, so given by this element, okay, so the coset in the W pi given by this. So the condition, discreteness condition here, refer to saying that this contains regular elements. And just means the following, so i.e., so it contains W such that this action of W on the basically the Lie algebra of M has no non-zero fixed point. Okay, yeah. So back to this formula for this discrete component of the local trace formula. Okay, so there's a, remember there's an expression like that. Okay, so here this is a certain scalar that is in some, basically it's a kind of combinatorial expression. So let me not write it down. This is actually just the centralizer of R in our pi. So in our case, we eventually specialize to real group. Then as Knapp has shown, the R group is actually abelian. So this is just R pi itself. While this is virtual character. Okay, so here with our test function as before, so this is product of the virtual characters associated to such a triple top. Okay, here, let me write down the formula for the virtual character. So here is this. So it's defined in terms of this normalized intertwining operator. So with tau, again, of this form, okay, then trace of the normalized intertwining operator and then acting on the parabolic induction of pi, okay. And then, of course, you define the operator on this using the test function fi, okay. Now, the reason for introducing this R group is that the characters of the R group correspond in a 1-1 manner to the irreducible component of the parabolic induction. More precisely, so the this virtual character is equal to this sum. So again, with tau as a triple like that. All right, here, where, as I said, the characters of the R group correspond in a 1-1 manner to the irreducible components of the parabolic induction of pi. Okay, so for such a character chi, I denote by pi of chi the corresponding irreducible component of this parabolic induction. Okay, so the virtual character is just a linear combination of these characters of irreducible representations. So overall, what one have is the following. So the geometric expansion of the local trace formula is in terms of semi-simple conjugacy classes. So overall, so the geometric expansion, so it's in terms of semi-simple, okay, a regular semi-simple conjugacy class in G of F, while the spectral expansion, so it's in terms of these, okay, and in particular in terms of only the temporal representations, well, a subset of the temporal representations of G of F, okay, so spectral expansion. So in terms of a subset of temporal representations of G of F. So in the global automorphic setting, so we know that the trace form is much more complicated. So for example, the geometric psi would contain terms that are not semi-simple. Okay, so in particular contain the terms coming from the unipotent conjugacy class, while in the spectral side there would be automorphic representations that are not temporal. But in the local cases are much simpler, okay? Yeah. All right, so now we would like to proceed with the stable version. Stable version. And this was also constructed by Arthur. Now, as we have said before, in the case of the invariant local trace formula, you have the geometric expansion in terms of the regular semi-simple conjugacy class. In the stable version, then, okay, actually, previously, let me first write down. Okay, so the invariant local trace formula is this one. Okay, while in the stable version, we would like to, for example, in the geometric expansion, replace it by the stable conjugate class. Okay? So the geometric psi, so the usual conjugacy, replaced by stable conjugacy. On the geometric side, while on the spectral side, but previously in the spectral side, you have temporal representations. Right? So, and in the stable version, one would expect that when you do the stable version, this would be in terms of, so it would be a sum over L packets. of temporal representation, which would, if we omit the local line length correspondence, this would be in terms of local line length parameters. All right, okay. So the general recipe for constructing this is, of course, the theory of endoscopy. Okay? So firstly, we briefly recall that, so given two elements, let's say G1, G2, GF, regular semisimple. Okay, then we, to be precise, strongly regular semisimple. Okay, so these are stably conjugate. If they are conjugate over the algebraic closure. GF bar. Okay, so our F is a local field, and stable conjugate. So if you take a stable conjugacy class, there will be a finite number of usual GF conjugacy class. So the stable orbital integral of a test function basically is just a sum of the usual orbital integral, where you take the the stable orbital integral respect to a stable conjugacy class is just sum of the usual orbital integral over those usual conjugacy class that are stably conjugate. And we say a distribution is stable if it depends only on the stable orbital integral of the test function. Now, given the invariant distribution as before, namely the spectral and geometric expansion of the invariant local trace formula, we would like to construct, as I said, the stable version. And the general recipe for doing this namely for constructing these distributions. So you want to construct the stable distributions S G prime, where G prime ranges over a certain set of groups associated to G, so namely the endoscopic groups of G. Okay, so distributes, and these, one for each such G prime, and this has to be stable respect to G prime, okay, such that, so for example, say you take the local trace formula as we had before, right? So we want to have an endoscopic decomposition where G prime ranges over the elliptic endoscopic datum of G, okay, and then certain explicit coefficients which could be computed quite simply from the dual group or from the L group of G and G prime. Okay, of this, but then you evaluate it at the test function f of G prime. So this is the Lang-Lang-Shelset transfer of f to G prime. Transfer of f to G prime. So on the face of it, this you can take this as an inductive definition, okay, of defining these distributions, okay. And the main point is that you need to establish that this is stable, okay. And this was, of course, also constructed by Arthur in his papers on the stable trace formula. So in the papers of Arthur, he did the stabilization for both the global and the local trace formula. So in particular, we have the following. So for the geometric side of the stable local trace formula, of the stable local trace formula, of course, in the p-adic case, one needs the transfer conjecture, so which was ultimately a consequence of the fundamental lemma. But in the Archimedean case, this could be, the stabilization could be done directly. Okay, so let me again first write down the formula. It basically looks quite similar to the previous case, in the invariant case. So except that the distributions have to be replaced by those that are stable. And the integral here is over the stable conjugate class. So capital delta refers to the stable conjugate class. Okay, G reckless elliptic. Okay, and then previously we have this in the invariant local trace formula. As I said, we have this modified version of weighted orbital integral, while in the stable version we have replaced by a stable version of these, which are once again defined inductively from these things in terms of Langlands-Shelder transfer. Okay, and to be precise, there's a factor here. N delta roughly is the number of usual conjugate class in the stable conjugate class delta. To be precise, really the Kopwitz order of the Kopwitz group associated with delta. Okay, so here this thing has an inductive definition. Okay, yeah. So namely that. Okay, yeah. So in these could be defined inductively in terms of these as follows. All right. So for such a stable conjugate class delta, this is defined as the sum over these previous distributions over those gamma that are stably conjugated to delta. This is the definition. And then these things are defined inductively in terms of this using the Langlands-Shelder transfer roughly as in here. Okay, so namely. So here the sum is essentially sum over those elliptic endoscopic datum of G that contains M as Levy subgroup. Okay, and then again these coefficients. Okay, yeah, again in terms of this Langlands-Shelder transfer. All right, okay. So this is a geometric side, and in the case when the Levy is G, then the terms, this one is nothing other than the stable orbital integral. Okay, so as before, if F is just a pair like that, then if the Levy M is just G, then this is the product of the stable orbital integral. Okay, here, this is as we've said, these are the stable orbital integral. It's just a sum of the usual orbital integral over those gamma that are stably conjugated to delta. All right. So on the other hand, for the spectral side, we have the following. Arthur obtained a formal formula for the spectral side, but it is in a way not explicit. The reason is very simple. As you remember, what we expect is that when you look at the stable version of the local trace formula, what one expects is that the spectral side would be a sum over L packets, okay? And if one admit the local Langlands correspondence, it should also be given in terms of the local Langlands parameters. But for a general group G and over a periodic field, we don't have the local Langlands correspondence available yet. Okay, so therefore, what one hopes to do at best is to have some kind of formal formula, which is what Arthur obtained in his papers. But in the case for real groups, okay, let me first write down some spectral side of the stable local trace formula. So Arthur obtained a formal formula. So namely that the formula he got, obtained a formal formula, is not really in terms of the Langlands parameters, but in some sense a substitute, formal substitute for that, a formal formula. So using formal substitute of length parameters. Of L parameters. Now, in the case of real groups, then of course we do have the length parameterization. And also, we have work of Shellstedt concerning the spectral transfer in endoscopy. So therefore, in this case, in the case of real groups, we can obtain a explicit formula for the spectral side of the local trace formula in terms of the in terms of the L parameter, not only the formal substitute. So let me first write down the theorem. So from now on, up to now, everything applies for p-adic also, okay? But from now on, we assume F is the real field. Okay? So therefore, we work with G of R and which of them?
Even in general, yeah.
Yes. No. So in fact, as was shown by our colleague Goldberg, so he showed that in the p-adic case, you do not necessarily have that. Okay. So yeah. For real group, that's fine. Real group, that's consequence of Knapp's work. Yeah. So without that assumption, there's as I say, you work with a central extension of the R group. So which makes the formula slightly more complicated, but you can still do it. Okay, yeah. Which is in any case in Arthur's paper, elliptic temper characters. Okay, yeah. So in any case, from now on, we assume F is R, and but to be precise, we really work with not with GR. So to be precise, this just for technical convenience. So to be precise, we work with the so-called K group associated to G of R. So K group, in this case, basically, you just a disjoint union of certain pure inner forms of G of R. So these pure inner forms correspond to the image of H1F GSC in H1F of G. So the main point is that you put together these pure inner forms so that the parameterization of representation in L packet takes a form that is the same as in the p-adic case. Okay. But this is just for technicality. Okay. So now let me state the theorem. So the theorem. So this is joint work with Chung Pang. So who is currently a postdoc with WeTech here, okay, at NUS. So as before, our test function in this form. So we would like a formula for the spectral side, or more precisely, a discrete component of the stable local trace formula in terms of L parameters. All right, okay, so let me first, again, write down the formula and explain. Okay, so let me explain. Okay, so here, so there are some definitions that are familiar in the in endoscopy theory. So firstly, I'll say, so phi ranges over the L parameters that are bounded because these correspond to temper representations. So here, so phi are L parameters. from the Lie group R to the L group G up to equivalence, and you require these to be bounded. Okay, and given such a parameter, you have the group S-phi, as usual, the centralizer of the image of phi in the dual group. And then you also look at S-phi bar, which is just a quotient of this by the center of G hat, more precisely the fixed element that are fixed by Galois, okay, which of course is G gamma R is just the complex, just Galois group C over R. Okay, yeah. And then this script S-phi is the component group of this thing. Now, so there's a certain condition which we call S discrete. It means the following condition. Okay, so in any case, let me first actually describe this. Okay, so phi 2. So these correspond to the parameters that do not factor through the L group of a proper Levy subgroup of G, okay, and these could be described in terms of a condition, okay, so namely those phi such that this S phi bar is finite, and they parameterize the discrete series representation of G of F. But as we've seen before, even in the invariant case, you have more contributions, okay, other than just the discrete series. So therefore, in the stable version, you also need a set that is bigger than this, okay, and it is this one. So it consists of those phi such that the center of the, so this group need not be connected, okay, so in general, this is a non-connected group. You take the identity component of that. So the condition we put here is that the center of this is finite. Okay, of course, if S phi bar is finite, then the identity component, of course, is just identity. So you certainly have this. Okay, yeah. Let me write here. Now, given such a L parameter, and if we use, say, Whittaker normalization, then there's a bijection between the packet corresponding to phi with the character group. Okay, and this is a point of, as I say, working with the K group associated G of R. So the L packet for K group, basically you just put together the representations in that correspond to different pure inner form of G. Okay, you put together these. Then if we work with K group, then there's a bijection with the character group of this. Okay, in general, if you do not put together the inner form, it's only an injection here. But because we work with K group, so you have this. And then the stable character, of course, is just a sum, right, over those pi in the packet. All right. And there's only one term that I did not explain, which is this. And unfortunately, this does require some time to explain. But suffice to say that this is a certain scalar. It is in fact a rational number. It could be negative in general, and it could also be zero. So this is a certain scalar. And this scalar is in general defined for any connected complex reductive group, because this is on the dual side, right? So complex reductive group. And these scalars were defined by Arthur in his paper, Unipotent Automorphic Representation. Okay, and it could be inductively, okay, could be inductively defined in terms of, again, certain scalars that I have not explained previously in the invariant local trace formula. So previously in the invariant local trace formula, there are again certain scalars, okay, that were defined in terms of, combinatorics coming from Bao group. Okay, and from these, one could inductively define these numbers, which are just, these were data just associated to connected complex reductive group, and it enters here. So when you are a discrete series parameter, so when SV bar is finite, so therefore the identity component is just trivial, then this number is just 1. Okay? Yeah. So in particular, as I say, when you only look at the discrete series parameters, then you have a shape that again looks like what we have before in the case when GF is compact. Okay, so okay, that's the formula. Let me just say a few words about the proof. I should also say that notice that there's also one advantage of working with the stable formula. So in a way, you can say that this becomes more simple than the previous invariant local trace formula. So in the invariant local trace formula, you have these virtual characters which were, whose definition is a little bit delicate in terms of this normalization, very delicate normalization of the intertwining operator. But in the stable case, in some way, it is, you can say that it becomes a bit simpler. Okay? Yeah. So let me just say a few words about the proof, main point of proof, and then I will end. As I say, okay, so you combine Shellstedt's spectral transfer for real groups, actually, yeah, spectral transfer for real groups, with the arguments in Arthur's unipotent automorphic representation. In Arthur's paper, combine this with the arguments in Arthur's paper, unipotent automorphic representation. Of course, in Arthur's paper, he deals with the global situation, which is, of course, much more complicated, but essentially the same type of argument works also in the local case. Okay, yeah. And so what one does is that you take this as definition, okay, you take this as definition and then show that it satisfies the inductive formula, okay? So, and then take this as definition and show directly that this inductive formula is satisfied. Okay. Okay, and with the, okay, then it follows that the discrete component of the stable local trace formula is indeed given by this one. Okay, so I think this is more or less, okay, so I finished it here. Thanks very much for your attention. So you see, we are actually, in some sense, working the other way around. So you take the Langlands classification, okay, classification of temporal representation in terms of parameters. You go back to the trace formula instead of what should be the other way around, instead of starting from trace formula and get the Langlands parameterization. But in any case, say in the p-adic and for classical groups, at least other than the type D situation, of course, we have the endoscopic classification available. So therefore, for p-adic and for classical groups, at least other than type D, the same argument goes. Okay, for these classical groups, at least, of course, I should I make a still thing. I should say that when we do the stable theory, everything is quasi-split, of course. Okay, so in the quasi-split case, again, you have these, the R groups are all very simple. They were just say elementary abelian 2 groups. So everything in the real case could be done directly for classical groups, other than type D. Therefore, quasi-split, other than type D, they were just elementary abelian 2 group. Type D is not necessarily true. Okay, so at least I exclude type D. Yeah. Yes. Okay. Yeah. Yes. Yeah. Yeah. Yes. Yeah. Yeah. Basically, you are excluding those. In some other call these elliptic. Let me just give an example. Take SL2. G is SL2. So of course, you have discrete series representation S discrete. Now, what you are excluding is, say, for example, the limit of discrete series representation. So that is not in S discrete. So we exclude that one. Okay, but that limit of discrete series it shows up in the invariant trace formula, in the discrete component of invariant trace formula. But when you do the stable version, that becomes excluded. Yeah, in that one.